previous videos, we defined vibration, how we collect, analyze, and make strategic decisions based on vibration analysis. Now it's time to shift wavelengths and dive into the actual characteristics of vibration. In other words, what actual characteristics can we measure to inform the strategic maintenance decisions? This week, the first question I had on my mind is what factors or forces shape the vibration signatures? We know vibration is, but what causes it?
So basically, when we talk about vibration, there's some certain things that affect how much something will vibrate. One thing is the mass, so how heavy something is. The heavier something is, the more energy it takes to get that moving, and the more energy it takes to keep it moving. So the mass, generally a heavier piece of equipment, this is right out of physics, it takes more energy to start that piece of equipment moving, but it also takes more energy to stop that piece of equipment. So the heavier something is, the more energy it takes to excite it, to take it. So that has a direct impact on how something vibrates. How stiff something is also has an impact on how something vibrates. Generally, if something's stiffer, it has a higher frequency, so that stiffness allows the piece of work, the machine, to go back, depending on how stiff it is. So that will dictate how much something vibrates also. Also damping, how something is damped. So when we damp something, what we're doing is we're actually isolating that piece of equipment from all the vibration around it. So if you've seen, lots of times if you're out in the plant and you look at a motor, and we're looking at a motor from face on here, here's the drive shaft. If you ever look at that piece of equipment and you look underneath the feet of the motor and there's a little rubber pad under there, like so, or sometimes there's a spring under these, what they're doing is they're damping that piece of equipment, or what they're doing, they're damping that vibration out. They're also, what they're doing is they're separating this piece of equipment from other pieces of equipment, so that the vibration from this piece of equipment doesn't affect the vibration in this piece of equipment, or the vibration from this piece of equipment doesn't cross influence another piece of equipment. So a lot of times you'll see if we have a bunch of pumps on a skid, like so, please forgive my drawing, what they'll do is they'll be isolated with these little damping pads underneath. And so what they're doing is they're isolating the vibration from this pump, from this pump. All those are factors that we consider when we, how much something will vibrate. Also, we can say in vibration, we'll say degrees of looseness in vibration. So depending on which way this piece of equipment might vibrate more in the horizontal direction this way than it does in the vertical direction this way, because of the weight of the rotor is pushing down this way, so it takes a lot more to get it to vibrate in the vertical direction than it does in the horizontal direction. So we refer to that as degrees of freedom. So we'll look at that where we're taking our measurements sometimes. We'll look at how something will vibrate, and we'll look at that. So a lot of times the excitation force will be the fault itself. So we'll have an imbalance, which at one time per revolution, the bearing, let's use a bearing as an example, will make a move. So that imbalance will be the excitation force. A misalignment may be an excitation force. A bearing defect might be the excitation force. So all those is what actually starts the thing vibrating. When you vibrate something at its natural frequency, and everything has a natural, it has many, many, many natural frequencies. If you vibrate something or turn something at its natural frequency, its ability to stay stiff or to stay together or not vibrate goes away. So if we had something that had a natural frequency of 1,000 cycles per minute, and we turn that at 1,000 cycles per minute, what would happen would be that the canceling forces, all these kind of forces work together, the stiffness, the mass, the damping, all kind of work together. So what happens is that your stiffness and your stiffness force and they're at the same kind of speed, and so that stiffness goes away. So if you turn something at its natural frequency, it shakes like crazy till it eventually destroys itself. Basically, a lot of what we call is the fault itself, whatever. If there's an outer race defect, inner race defect, ball, they're all excitation forces. Some of the other faults we look at, misalignment, imbalance, looseness, eccentricity, bent shaft, all these other things, any one of them could be an excitation force that would cause that vibration to increase.
It's interesting here that the machine fault is often the exciting force that displaces the machine from the place of rest. So if we build a perfect pump and balance it perfectly, align it perfectly with the world's greatest lubrication, and we pump fluid that's at room temperature or at the machine's temperature, it should run forever. Right, Paul?
Even with the best lubrication of the world or whatever, there's still going to be some friction in there, and it will not. I mean, a good bearing, proper lubrication, proper clearances, proper fit, all that stuff should run for like 25 years. Did we ever see a bearing run for 25 years? Never. And so what it is, so there's always going to be some contamination of the fluid. There's always going to be a wee bit of friction. There's always a little bit of imbalance. Always. It doesn't matter. You cannot perfectly balance something, because if you think of that shaft that we balance, there's always gravity pulling down on that shaft. So when we talk about something being balanced, all the weight is perfectly centered around the center of the shaft, perfectly centered. So when we have gravity pulling down on this, pulls the shaft a little bit down, so there's a little bit of weight, more weight on one side of the shaft than the other, regardless. So it's always going to have some vibration in a piece of equipment. The only place that you could have zero vibration like that is in space. So if you went up in the space shuttle and set that up in there with no gravity hauling down on it or anything, then you could have that shaft turn perfect. But we're always going to have some imbalance because of gravity pulls down on that. The heavier the rotor is, the more imbalance that you will have. Also, when you leave a rotor sit there for days on end, and I've dealt with rotors that weigh 60, 100 ton, what happens is they sag, so they bend a little bit. So then in order to get the imbalance, so already you have imbalance in that, so you have to run that for a while to take the imbalance out of it. So when you start that up, there's going to be more vibration. Then as it warms up, everything gets up to temperature, and that the sag comes out of it, then the vibration will go down a little bit. Never a situation where there's never any vibration.
Okay, fair enough. Let's look at the spring mass example and draw out these forces on a visual diagram from a book.
I have 5 different states of a sine curve, or a period or one cycle of vibration. In the top example, A, there is, you see A to B, there's a small weight representing imbalance. And in the first example, it's at the 3 o'clock position and it's rotating counterclockwise. So B, it's getting to the 12 o'clock position, C, 9, D, 6, and then E, it returns back to the same point. So in this example, the large block represents the mass. The spring represents the damping force of the machine, or its resiliency to return back to the state of rest. And the block that it's with the cross section that it's hanging from would represent the foundation. So this is a really good illustration of if we have that mass at rest, and then the excitation force, which is the imbalance, goes to the 12 o'clock or the vertical position, the spring is going to compress and the weight is going to move up, which is graphed on the right with the upper limit, neutral position, and lower limit. Now these upper limit, neutral position, and lower limits are only in the vertical direction. As the weight goes from the 3 to the 9 position, it's not being graphed here. So this would be as if we were taking our vibration readings with the accelerometer mounted vertically. So it's only going to pick up the vibration that's happening in line with the vibration measurement device. So an excitation force would be the rotation of the imbalance inside of the mass of the machine that pushes that mass up and down or from its state of rest in one cycle. And what Paul is trying to emphasize here is that each one of the components in the machine is going to have one of these vibration signatures, and they can all work together in time at one specific natural frequency, at which point all of those excitation forces are all working together at the same time and can really amplify the amount of severity of vibration that you're measuring.
The vibration characteristics we're going to cover from the sine wave are going to be frequency, displacement, velocity, acceleration, spike energy, and finally phase. Let's start with vibration frequency. There are a lot of time-based terms in vibration analysis, like period, frequency, cycles per second, cycles per minute. Let's get Paul to explain how these all relate to the vibration analysis that takes place.
So this axis here in the sine wave, this represents the neutral position. Definition for vibration is back and forth from its position of rest. So there's our back and forth movement, one complete turn, one cycle of vibration. So what we do to figure out what the frequency is of this, and remember every fault has a frequency. Outer race would have a frequency, inner race would have a frequency, ball would have a frequency, cage would have a frequency. They all have their own frequency. So how we figure out what the frequency is, on this line here, this represents time. So what we do is we take the time that it takes to complete one cycle of vibration, and we divide that into one. So our frequency formula is frequency equals 1 over time. This time has to be in seconds, okay, for this formula to work. So generally, a lot of times what will happen is if you think about how fast that outer race is turning, you're running 1,800 revolutions a minute. One revolution of that outer race takes way less than 1 second. Like we're talking milliseconds, so thousandths of a second to complete one cycle. So if we have something that's in milliseconds, so if it was 20 milliseconds that we had for the time, we got to convert that time into seconds. So milli just means 1,000. So 20 milliseconds would be 1, 2, 3 would be 0.02 seconds, okay? So then what we do is we take that time in seconds, divide it into 1. So I don't know, whatever it is, we take 1 divided by 0.1 of a second, like this. It gives us 10 hertz. Hertz in vibration is cycles per second. There's cycles per minute, and there's hertz, which are cycles per second. You want to change cycles per second, which is hertz, to cycles per minute, you multiply by 60. When you want to change cycles per minute to hertz, which is cycles per second, you divide by 60. Okay, so with hertz and CPM, cycles per minute, hertz is cycles per second, they're exactly the same thing, we just make the conversion. But when you have cycles per minute, it's easier to relate to certain faults.
That makes sense. If we're running a machine at 3,600 RPM, it's a lot easier to just diagnose the vibration frequencies if they're written out as 3,000 CPM and not 60 Hertz. There's no translation. We're just speaking kind of in our native language. So we know the units of vibration frequency. How can we use that as a diagnostic tool?
Imbalance, misalignment, looseness, bent shaft, eccentricity, all happen at a direct multiple of running speed. So if we look, it's our spectrum, we'll talk about this 1 times running speed, 1 times. Imbalance happens at 1 times running speed and 1 times running speed only. So if I see something at 1 times, I know it's imbalance. If I see a peak like this and I see a peak at 1 times, let's just say that it's just running at 1,000 cycles per minute, this machine. So 1 times is going to be 1,000 RPM. 2 times is going to be 2,000 RPM. Misalignment happens at 2 times RPM. So we know misalignment happens at 2 times running speed. So that's how, when I think about something that's loose, looseness happens at 5 to 10 times multiples of running speed. So if I see 3, 4, 5, 6, 7, 8, 9, 10, 11, see 11 times, check this one, it's 11 times running speed. I hope you can see that. Then I know it's looseness. Bearings always happen at some kind of integer multiple or a fraction of running speed. So if I have a bearing and I see a peak here in my thing and this is at 5.6 times running speed, then automatically I know that that's a bearing, because the bearing is only one that shows up at a decimal of running speed. The bearing is designed so it never comes up at a direct multiple of running speed. That's the way they're made in the factory, so that you're able to differentiate. So that's why a lot of times I like working like that. If you work in hertz, doesn't come up like that as multiples of running speed. But in CPM, if I know running speed's 1,000 and I see something coming up at 2,600 cycles per minute, right there I know it's not imbalance, it's not misalignment, it's not looseness, it's a bearing, because it's not an exact multiple. So like a squeal, a rub, something like that shows up below 1 times running speed, so subsynchronous. So a harmonic is just that you have the fundamental frequency. So let's say for looseness, okay? So the fundamental frequency for looseness might be it's a multiple of 1 times. And then so when they would have harmonics, would be just other peaks that are exact multiples of that first peak. So a harmonic of this at 1 times, we're at 1,000 CPM, harmonic would be 2,000, 3,000, 4,000. So it's just a multiple of the fundamental frequency. So the outer race has 5.6 times running speed, right? Harmonic of that would be 2 times 5.6, which is 11.2. And then the next one would be just another multiple and another multiple and another multiple. So, and also the harmonics, the more harmonics there are of that fundamental frequency, the more severe the fault is. So that's one way we can also dictate how long that piece of equipment is going to last by how many harmonics it has of that fundamental frequency. So something gets the only one that really has no harmonics of the fundamental frequency is imbalance. Imbalance will show up at one time only. There won't be any harmonics of that. But a looseness, there would be 5. That's how we tell looseness. The more harmonics there are, so looseness or whatever is just a multiple of running speed. So if I have a harmonic at this is 1,000, so we got 1,000, 2,000, 3,000, 4,000, 5,000, 6, 7, 8, 9, 10, 11, 12,000. The more harmonics there are, the looser I can tell that that piece of equipment is. So harmonics are really, really good for telling us how long something will last. Anything subsynchronous, like growling noise, you know, all that. Also subsynchronous vibration with the bearing. In this last stages of vibration, what you'll see is a lot of noise down below 1 times of the bearing. So that just means that you've basically lost your fit, you've lost your clearances. That bearing is just getting ready to calf like today. It's right. It's at the very last stages. So subharmonics and harmonics all tell us about how long a bearing will last by. And you don't learn that overnight, I can tell you that. It takes a while. You got to look at a lot of spectrums to get that stuff down.
We don't really get this beautifully smooth sine wave when you take a vibration reading. The graphs I've seen kind of look like the ones of charts of an earthquake or an ECG. Is there any value that can come from these kinds of scattered looking charts or plots?
Okay, so certain waveforms can tell us certain things, these complex waveforms. So for instance, if I had a waveform that went like this, come down like that. So something like if we had a missing gear tooth or something like that, this has all the vibration from that gear in it, has all the vibration from the bearings in it, has all the vibration from everything in that piece of equipment we took a reading on. So we have a complex waveform. But if I had a broken gear tooth, I measured the time between, we call these impacts. They look a certain way in the waveform. So I measured the time between here, take that time, measure it, get a frequency, and then if it was a broken gear tooth, it would be 1 times the frequency of the gear with the broken gear tooth. Every time that gear would go through the mesh, there'd be the big bang, because there's a broken tooth, and it would come out of the mesh, take another revolution, bang, take another shock. And so as soon as I see a waveform like that, and I'm looking at a gear, I know that I have a broken gear tooth. I don't have to do any other measurement. I don't have to do anything. I can just tell by the pattern that it shows.
So that complex vibration pattern, also known as the time waveform, can tell us a lot. Our vibration data collector and software can also distill that waveform into individual frequencies. If we know that data, we can look at diagnosing even more faults. What are the different types of faults, and what are they a symptom or a sign of?
If I had a inner race defect on the bearing, if you think about it here, what happens with this? If we have a defect on the inner race and the outer race is clamped, what happens to that defect on the inner race? Right? Sometimes it goes through the load zone, sometimes it's out of it. If we had a mark here in our bearing, I don't know if you can see that, it's in the load zone, it's out of the load zone, goes in through the load zone, comes out of the load zone. So I can tell by this, every time that bearing goes, the roller goes through the load zone, there's a little less clearance, so it makes a modulation. So this is what we call modulation of the waveform. So all I do is I see that modulation, I'm looking at a bearing, I know I got an inner race problem, because the load zone is always changing, or not the load zone is always changing, but the fault goes through the load zone, comes out of the load zone, goes into the load zone. Every time it's in the load zone, more vibration comes out of the load zone. Now, if I had the same bearing and I had an outer race defect, think about this bearing, the outer race is fixed. Wherever the defect is, it never moves. It doesn't go through the load zone. It stays in the same location. So that waveform would look like this. Be the exact same above and below, okay? That's another thing, how we can tell how severe a bearing is. If you've got way more movement on one side of the waveform than the other, so that they're not the same in either side, that's another example of how severe the bearing is. So that's another indicator that we could just get from the complex waveform. I haven't done any analysis. I don't know what frequency, I know nothing. I'm just looking at the waveform, raw waveform from the box, and I see that one side is goes way farther than the other side from the neutral position. Once again, that's an indicator of how severe your bearing fault is. So that complex waveform, just by looking at the waveform, can tell you a lot of stuff of what's going on in that piece of equipment, okay? We take that complex waveform, we separate it out to look for individual frequencies, but just the pattern of the waveform alone can tell you broken gear tooth, inner race defect, modulation. We look at, okay, what causes it to modulate, right? As the fault goes through the load zone, more vibration, goes up, comes out of the load zone, less vibration. So we get this zzz, 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 kind of, so you can tell different things by that. So it's all kinds of different things we can tell. Once again, years of experience to figure that stuff out. That's not something you learn today, kind of thing, right? All the stuff I learned was from the old guys that I started working with. They told me all this stuff. It's not in books. No, a lot of the stuff's not in books. Some of it is, but some of it's not. It's just by experience or whatever.